welcome to another episode of the Data Science Decoded podcast. I didn't see you, Mike and Nir, since last year, which is a joke by Mike, so now I stole it. How are you guys?
I'm okay. By the way, it wasn't a joke. I really haven't seen you guys since 2024. So it wasn't a joke. And I'm okay, still recovering, but 95% percent recovered from my virus, maybe COVID, I don't know. And I'm pretty excited to talk about this paper. This paper is really cool, not very tough mathematically, so I'm pretty excited about it.
Perfect. And how are you, Nir? Kudos on the hat. You look lovely.
Doing good, thank you. Yeah, I said I will try a new hat, and you know that I like hats, so I'm trying this hat now. Yeah, I'm doing good.
Perfect.
I'm doing good. I'm looking forward
Perfect.
for talking about dynamic programming. I was also recovering from some asthma attack, but now I'm better,
Wow.
and I'm locked and loaded for discussion.
Perfect.
By the way, you love hats, and I love shows. I have about 15 pairs of fancy shows.
You mean shoes? Shoes? You mean shoes? Yeah.
Shoes.
Nice.
Not shoes.
Nice.
Sorry for my English. And I love shoes, but you can't see it now.
No, you can. You have to love something that you can see on the podcast.
Yeah, I love gold.
Like paper. You like papers. You
True,
like gold.
true. Great. So to our listeners, welcome back to a new year of our podcast. It's the 22nd episode, and we have today a paper titled "The Theory of Dynamic Programming" by Richard Bellman from 1954. And some background on Richard. So he grew up, I think, in the States to a Jewish family, and did his PhD around the Second World War II. He was part of the project in Los Alamos. I think he helped them with some physics stuff. But again, he's a mathematician. And then afterwards, in the early 50s, he formulated the dynamic programming framework in the paper that we're going to cover today. Funny or interesting fact, Mike and Nir and the listeners, are you familiar with the curse of dimensionality? Right? Mike, can you give us a few sentences? What does it mean?
Okay, curse on the dimensionality is a phenomenon that, in very simple words, can be explained as far as the dimension of your space, as far as the dimension of your data grows, everything becomes distant. There are nothing close in the very high dimensional space. So if you want to train some model in very high dimensional space, you need a lot of samples, and the number of samples grows. I don't want to say exponentially, but it grows very substantially with the dimension of your data, and that's why it's called curse. We want to train a model in very high dimensional space, and we need tons of data.
And you know who coined the term curse of dimensionality?
I guess Bellman.
Exactly.
I have no idea.
Yeah, that's why I asked. Richard here in this paper talks about it, but the actual term first he introduces in the following paper that he did from 1957. But also here we're going to cover it. He talks a little bit about dimensionality. So that's a cool golden nugget that I found. So
nice.
I was excited to share with everyone. So perfect. Let's start with the paper. I think there's like 10 chapters, but we won't go over all of them. Around 4 or 5 are examples. So we'll go more in depth on the first ones when he introduces the concepts. And I'll start with the introduction, which is important. So he says, Before turning to a discussion of some representative problems, which should permit us to exhibit various mathematical features of the theory, let us present a brief survey of the fundamental concepts, hopes, and aspirations of dynamic programming.
What a sentence. What a
yeah. Today we don't get this. He says, to begin with, the theory was created to treat the mathematical problems arising from the study of various multi-stage decision processes, which may roughly be described in the following way. We have a physical system whose state at any time t is determined by a set of quantities which we call state parameters or state variables. At certain times, which may be prescribed in advance or which may be determined by the process itself, we are called upon to make decisions which will affect the state of the system. These decisions are equivalent to transformations of the state variables, the choice of a decision being identical with the choice of a transformation. The outcome of the preceding decisions is to be used to guide the choice of future ones, with the purpose of the whole process that of maximizing some function of the parameters describing the final state.
By the way,
so again,
by the way, if this paragraph reminds you, I'm talking to our listeners, if this paragraph reminds you of reinforcement learning, you are totally spot.
Yeah, that's why we chose the paper.
What topic?
Reinforcement learning.
Because what is described in this paragraph is actually a reinforcement learning problem or technique, or
Yeah, because to me, as the concept of multi-stage decision making, right? That's where his framework fits in. And he says examples of processes fitting this loose description are furnished by virtually every phase of modern life, from the planning of industrial production lines to the scheduling of patients at a medical clinic, from the determination of long-term investment programs for universities to the determination of replacement policy for machinery in factories, and so on and so forth. It's abundantly clear from the very brief description of possible application that the problems arising from the study of these processes are problems of the future as well as the immediate present, which is also a cool sentence. Yes. Turning to a more precise discussion, let's us introduce a small amount of terminology. And he says a sequence of decisions will be called policy. And a policy which is most advantageous according to some pre-assigned criteria will be called an optimal policy, right? And this is the terminology we use today as well.
Yeah. The only thing which is absent here in all these 2 or 3 paragraphs is a reward. He's talking about some function which is employed on the final state, but this function which is employed on the final state, we can loosely refer it as to some reward.
We'll get there. Soon he'll get the rigorous mathematical definition, and then we can talk about it. And he says here, the classical approach to the mathematical problems arising from the processes described above is to consider the set of all possible sequences of decisions, which is to say, the set of all feasible policies. Compute the return for each such feasible policy, and then maximize the return over the set of all feasible policies. So in a sense, calculate everything that is possible to calculate. That's like the classic approach.
By the way, Daniel, you mentioned the coordinate dimensionality. Can you see something, some silhouette of coordinate dimensionality here in this sentence, in this paragraph?
Yeah, so the red one that I'm going to read now, that's underlined to our viewers, they can see it.
I didn't read it. Now I'm reading it.
To our listeners, I'm going to read it now. He says, it is evident that straightforward and reasonable as such a procedure is, it is often not practical. For processes involving even a moderate number of stages and a moderate range of choices at each stage, the dimension of the resultant maximization problem will be uncomfortably high. with continuous processes requiring maximization over function space. So yeah, that's exactly the problem of, let's say, brute force, calculating all possible policies over space that of possibilities.
Yeah.
And
Daniel, it's a
yeah,
very small remark. I just saw that he used the term uncomfortably high. Today we are
yeah,
not using uncomfortably high. Today we are using prohibitively high, and it is interesting why it changes this way. It is not related to political correctness or something like that. It's interesting how uncomfortably turned to prohibitively.
Mm-hmm.
I think it's just different times. Maybe they use
Yeah,
different
different times. Our
words.
times are more whiners.
Yeah.
One can devote himself to do that, even if it's uncomfortable.
Okay.
That's what he means.
Maybe.
And now there's a paragraph for Mike, and he says, if we momentarily re-examine the situation, not as a mathematician, but as a practical man. So you see, Mike,
But I'm
he's not a mathematician.
I'm a practical man. Former mathematician is a practical man, no?
No, that he says there are different things. And he says, we see that this price of excessive dimensionality, a price that occasionally makes even a modern computing machine cringe, arises from a demand for too much information. How much information is actually required to carry out a multi-stage decision process? Again, there's the use of information. Probably it's not Shannon information.
And note that he's not complaining about lacking data. He's complaining about lacking information.
Although I'm pretty sure you can formulate it in some kind of information theory perspective.
I think he is. I think he is referring to information theory.
Oh, okay.
That's what I
Because he did.
Yeah.
I didn't see that he cites Shannon.
No.
But for
I
sure.
mean using information instead of data. That's what I mean.
Okay. But it's more like using the colloquial term of information.
Yeah. What I'm trying to. I think what I'm trying to say is that the person who writes in this manner, he's speaking word for word, at least in my view. And if he's actually doing that, then the word information has a meaning. That's what I think.
Okay.
Interesting.
Yeah.
And now continue. He says or asks, do we require knowledge of the complete sequence of decisions, those to be performed at the present stage, those at the next stage, and so on? Not at all, he answers. It is sufficient to furnish a general prescription which determines at any stage the decision to be made in terms of the current state of the system. In other words, if at any particular time we know what to do, it's never necessary to know the decisions required at subsequent times. Okay, so it's like he's starting to break the problem to smaller problems. That's as far as I can tell. And now he says, donning our mathematical cap again, so he's a mathematician again, we see that this common sense attitude reduces the dimension of the problem to its proper level, namely the dimension of the decision problem that confronts one at any particular time.
By the way, this approach is very real life anchored approach. You don't start doing your PhD from writing your thesis. You need to do your BSc and MSc and learn a lot. So you need to move step by step. And this step by step movement, that at each point of your life you decide what to do, condition on the state you are in. It is very reasonable and very smart, and I think it is the only approach that a man can proceed in the life.
Yeah, I would agree. He tries to formalize how we humans, agents in an environment, also interact with environment to some degree. By the way, later in his career, he moved into biology more. Yeah.
Interesting.
So I'll continue now. The second chapter. The title is the fundamental approach. Yeah.
I have a question. The mathematical.
For sure, Mike.
The mathematical cap is this?
By the way, I have a similar one. Maybe
Nice.
I'll bring it in soon.
Nice.
So you need to buy me one because I don't have it.
Uh,
I
Yeah.
can send you some shoes if you.
Offer. For our next episode, we all will be wearing matching hats.
Let's do it.
Perfect. Yes, I'll continue with the second chapter. The title is The Fundamental Approach. And here he introduces the framework. And he says, as stated above, the basic idea of the theory of dynamic programming is that of viewing an optimal policy as one determining the decision required at each time in terms of the current state of the system. Following this line of thought, the basic functional equation given below, describing the quantitative aspects of the theory, are uniformly obtained from the following intuitive, right? So he has a principle, which is an intuitive one. It's titled Principle of Optimality. Bless you, Leo.
Sorry.
And the principle of optimality states, an optimal policy has the property that with whatever the initial state and the initial decisions are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decisions. So Nir, can you give us some explanation and motivation? What does it mean to you?
It means that given the initial, when I read all these first pages of text, what I was thinking about is the theory of dynamical system control theory.
Yeah.
And not data science and machine learning like you guys.
I'm with you, Nir, I guess. I wasn't thinking about machine learning here.
And given, at least in deterministic systems, which is covering right now, given an initial state and the dynamics of the system, which is deterministic, at each time step, we can make a decision to the following time step, and we can judge everything. We can judge everything by running through these iterations up to the final time step and see if we're optimal. And if we're optimal, it means that we are we took the right decision at every time step, the optimal decision.
So that's the optimal policy from the space of all possible policies.
Yes.
Or you can think about it again, decisions you can make.
Yes.
And again, policy is a vector. We're going to define it of decisions in each step.
It's a function.
You have
function.
Yeah, it's a function, exactly. And you have large amount of those policies. There's one that it's optimal.
Yes.
Okay.
Let me give you an example.
Not necessarily one, by the way. It can be many. It depends.
Yeah, it's the one that maximizes. That's true. It's not a unique one. True.
Yes.
Good point, Mike.
Yes, and I think it's this principle of optimality. We can learn something from it to life, for life.
Oh, I love that.
Which is when we are, let's say, Mike gave the example. There are plenty of examples, but Mike gave the example of students, or engineering students, or math students, or physics students. Doesn't matter. So you're saying, okay, let's go to college because in 10 years from now, and only the animal that is called human can do that in inference. 10 years from now, we will have a nice job and we can support our families and so on and so forth. Okay, and every decision along the way, like doing this homework or not doing this homework, or playing video game, or improving the 56 I got on this course, or leaving at 56, can be
going
judged.
To the gym or not going to the gym.
Going to the gym or not going
it's
to the
easy. Go to the gym.
Exactly. Can be judged 10 years from now if we are patient enough to actually wait this process out and judge it 10 years from now in retrospect. And this is exactly what he's talking about right now.
Yeah. Love it. Thank you. So he continues. The functional equations we shall derive are of difficult and fascinating type, wholly different from any encountered previously in analysis. Nonetheless, as we shall see below, they have be utilized to provide an entirely new approach to some classical problems. So it's an interesting claim. He says, different from any encountered previously in analysis. So again, I don't know the history, but like this is the first time this was formulated.
Yeah, at least
Which
ChatGPT told me so. I didn't check it, but if we can rely on ChatGPT, which I'm not sure we can, but it is a quite simple question, so maybe it is right.
no, we can also rely on Bellman, but
Yeah.
it's still fascinating because the math here is I wouldn't say straightforward, but it's quite basic. Again, before you go to variational
Relation.
calculus and stuff,
I
but
have
the
a question.
basic one. Mm-hmm.
If we do some sort of a, I don't know, let's call it a thought experiment, and take our
Mm-hmm.
GPUs of the present and shift it back in time to Bellman, do you think they would still optimize like that, or the dynamic programming part of math would never be developed?
I think it would have been developed because we need dynamic programming now, because you can't train your robot without reinforcement learning, because the dimension of the decision space is prohibitively or uncomfortably high. So we still can't do it with a brute force approach. So I think it would have been developed. I don't know when, but the fact that we still need it now, I think it is a necessity.
Okay.
Yeah, sounds reasonable to me. Also, before going in the math, I want to say that it reminded me like, to me, I felt like this concept of optimality, principle of optimality, that you can break this one big problem into smaller problems, uh, somehow gives me the intuition of linearity, right? I don't know if you thought about it, like if you're thinking about systems, and like if it's a linear system, so maybe you can break it down into smaller ones, and then you just like multiply each small step, which is a matrix, whatever you formalize it. But when I thought, like, if it's a non-linear process, can you still apply the concept of optimality? Probably, right? Because it's a general concept, but I don't get the intuition. Like, to me, the intuition, I can break something into smaller parts and calculate each one independently, means linearity to a degree, or something like that. What are your thoughts on this claim, and what am I getting wrong?
I don't know what you're getting wrong. I don't agree with you about the linearity.
Wait, you disagree or you agree with me?
No, I disagree with you. I don't think that the process which can be partitioned into several sub-processes has something common with the linearity. It is for me, it is unrelated to the linearity. It's just a property of the process. But there are some processes which you can't divide, which you can't split into sub-processes. So these methods can be straightforwardly applied to any process.
Yeah, I know that's the case. I'm not trying to get the intuition. Why am I'm having like a mistaken intuition?
I think
you can think about sequential decision making. Okay, if you can if you can build or construct or split your processes into some decision sequence decision problem, you don't need any linearity. You need this step-by-step decision making, and it has nothing to do with linearity, at least for me.
Yeah. It's just to reinforce what Mike said. In this paper, I don't think Bellman assumes linearity at all.
No.
Yeah, and I think that what you are, Daniel, referring to is what we learn in a lot of engineering and math courses. Let me give you an example. Okay, Kalman filter. Kalman filter is an iterative minimum mean square error estimator, which is working on a time step basis. So it's a lot of, reminding us a lot of this. In every step, it's minimizing the mean square, okay? Error. And it's a Bayesian type filter. And what do we do when the dynamics are nonlinear in Kalman filter? We have a few options, but the most most highly used one is to linearize. To take time steps that are very, very small.
Yeah, they're very small. That's what
Exactly.
I feel
And
here.
they say, okay, it's linear. It's linear.
Exactly.
Yeah, and who actually invented this approach? Gauss, right? In the Gauss-Newton algorithm, it's not nonlinear least squares linearized around the current estimate. Okay, and
So I feel why it's not the same here. Why can I break it arbitrarily into smaller?
You can do it. You can do it. But if it's very highly nonlinear, even a small step will accrue an error that you don't want.
Yeah, exactly.
And then, and we know from math that doing this process does not guarantee optimality. And he's talking about optimality here.
Daniel, maybe you're confusing. I still don't get it, but I know that we are using Taylor approximation when we have non-linear propagation of our processes, but still we can use it blindly in any case. For me, we can have linearity, and in many cases we have this linearity in the rewards. So your reward is cumulative, and if your reward is cumulative, you can just sum up your rewards to get the total reward. So in this relation, in this context, this split of the process into sub-process can be regarded as a kind of linear, you know.
Okay, now I get what you're saying. Okay, thank you. Let's continue. And now he formalizes the discrete deterministic process. So that's chapter number 3. And now he defines, he says here, let us begin with the simplest case of deterministic process, where the system is described at any time by an m-dimensional vector. So we have a vector p that is m-dimensional from p1 to pm. And it says it's constrained to lie within some region D, that's cool. And now he defines capital T, which is a transformation. And Tk runs over a set of which might be finite, enumerable, or continuous. A set of transformation, that's why it's T. And the property is that where you apply those transformation on each step, you still stay inside this D space or region.
By the way, in the reinforcement learning jargon, this T is just a space of our actions, because the space of our actions just transforms any state from the state we define into another state.
Yeah, and now we can think of an n-stage process. So that's the n decisions you take, or n transformations. And the idea, he says, to maximize some scalar function after this n stage process, which he terms R of P. So I think R is reward, and P of the final state.
Yeah.
And we shall call this function the n stage return. So maybe it's R for return and not reward, but okay.
Yeah, equal the return.
Okay.
And a policy, now it defines, consists of a selection of n transformations. So capital P is a policy. It's always from T1 to Tn. So at each stage we do a transformation up to n. And then we have also different states, because different n states, because we apply n transformations one by one. And then he talks. He says,
a small remark is he's defining here the policy, which is a function which defines in the deterministic case, it defines exactly the action, and in the non-deterministic case,
it's the expectation.
It hasn't the expectation, can be some probability of some of some action, but look, then I'm reading it, and I'm thinking of Markov decision process, because any of your action depends only of your current state. It doesn't depend of any former state. So all the information you need to build your optimal policy is the current state. So we have this Markovity here without mentioning.
Yeah, I think what you're referring to is MDP, Markov decision process.
Yeah, exactly.
That's what it is.
And it's also like the basics of reinforcement learning, and it was introduced the MDP in 1960, so a few years later, but it's really based on this idea.
What by not by Bellman, right?
No, by Howard something, by Ronald Howard.
Okay.
Yeah.
Maybe it's a future paper to review.
By the way, good paper for one of our next episode.
Yeah, maybe for a future we should review it.
Guys, a question or a thought, maybe. When I'm looking at this, I'm thinking in the most simplistic way, that's exactly how we do gradient descent, right?
Like we're not there, so I want to finish and then we can discuss. It says the maximum value of R of Pn, which is like the return function determined by an optimal policy, will be a function only of the initial vector P. And so that's where we started. The number of stages, capital N. And now we define this function which maximizes R of this Pn over all possible Ps. And he says the end state, which he defines this function, which is Fn, the end stage return obtained using an optimal policy starting from the initial state P. Okay, and that's what you wanted to say, Neil, right? It reminds you of some kind of optimization process.
Yeah, the gradient that we use in let's say neural network. When it's, first of all, we use the back propagation process. Every stage of this back propagation process reminds me of one stage of this process that he defines here.
But I'm trying to understand, but I get that this is an optimization process that is recursive, but you don't propagate anything. There's no error. There's no...
Oh, there is an error, right? Because we are evaluating the gradient of the cost function. At this stage of at this iteration.
Where's the gradient here? I'm missing something. There's no...
He's not referring to gradient at all.
Okay.
Just reminds me.
By the way.
Reminded. Okay, reminds you. Okay, I thought you see an analogy.
No. The gradient descent process. It's not even the back propagation. The gradient descent, like the iterations that we do there, reminds me of this iterative process, in which we are minimizing the cost function, and we will arrive, if the cost function is let's say convex, then we will arrive at some global minimum or minimum if we continue with the gradient. I don't know if it's a valid analogy, but this is what came to my mind.
To me, that's an I get the optimization that happens here. I don't see the analogy to gradient descent.
Okay.
What do you think, Mike? You see?
I don't see here an analogy to gradient descent. Gradient descent is sometimes used as a part of determining of an optimal policy, but still the process itself, the nature of reinforcement learning, which is discussed in this paper, is not just gradient propagation. I think it is a bit more of it. So I don't see some straightforward application of gradient propagation here. Maybe I missed something. I don't know.
No, maybe I missed something.
Yeah, and then he says that there is a recursive process. So because this Fn, which is the end stage return, is maximizing the return function of the state at the end stage. But the state at the end stage is the state, just the taking the stage n minus 1 and applying a transformation on it. Again, because we broke it into smaller stages. So he's saying now there's a recursive process here that happens.
By the way, he's talking here about the sparse reward scenario. You get your reward only at the last stage. You don't get any rewards here.
Yeah. And this is an interesting paragraph that I want to read and hear your thoughts. He says, it is clear that a knowledge of any particular optimal policy, not necessarily unique, as you already said, Mike, there could be more than one, will yield Fn of p, which is unique. Okay, Fn of p is like the reward or return function. Conversely, given the sequence Fn of p, all optimal policies may be determined. So he says, and I would like to hear your thoughts, we thus have a duality between the space of functions and the space of policies, which is of great theoretical and computational importance. This point will be discussed again below. So he says there's duality. Fn is like, I don't know, our function we're trying to maximize, it has some value that we can achieve. And there's also space of all possible policies, and out of them there is an optimal one. And somehow he says there's duality between space of function and space of policies. Do you get what he means?
I don't get what he means here.
Because he says it's of great theoretical and computational importance. So I'm like, I'm trying to wrap my head.
Yeah,
maybe it relates to your sparse reward point.
I don't know, because these functions are actually policy. What is policy? Policy is a sequence of functions. If you assume that you have n point decision process, then you have n points in which you have to build a policy, which is conditional on your current state. So this function and these policies are more or less the same, and you just need to pick to somehow build or determine the optimal sequence of functions, and this is the optimal policy. So I don't know what is what he means here, but I'm very far from being an expert in reinforcement learning. Very far.
Yeah, I understand it a little bit differently. I think this paragraph is mentioning a if and only if relationship between the linear or nonlinear transformations or functions plural, and the policy. So he's saying if we pick the optimal policy, this will yield a unique Fn of p. And conversely, like the other way around,
if we have a unique,
that's the if and only if we have this optimal policy, it will take us to a unique Fn of p. And I think that's what he means here. I don't necessarily appreciate the maybe I don't appreciate the great theoretical and computational importance, because I'm not an expert in dynamic programming at all.
Yeah.
Far from it. But I think that's what it means, at least.
Okay, so there are a few more chapters where he now adds more complexity, like stochastic case, a non-deterministic, and some examples. We won't go over it due to time, but I would like to hear your thoughts about what do you think and how do you see, and we touched upon that, how this dynamic programming relates more to machine learning and reinforcement learning. And the second question, have you ever encountered it in other domains?
Before we answer all your questions, I want to ask mine. Okay, I
Okay.
think it's a bit simpler.
Yeah, so that you're a good Jewish person.
Yeah. And we have plenty of iterative algorithms, but some of them are not dynamic programming algorithms. Do you know which iterative algorithms are not dynamic programming algorithms? What is the condition which must hold in order to iterative algorithm to be dynamic programming algorithm?
That's a great point, and I thought about it myself, and now I'm not sure.
I think in my opinion, it is about the state, because in the dynamic programming, your decision depends on the state, and in many iterative algorithms, whatever you get at stage n, you do the same. You do the same. Your computation, maybe your result may be different because the result of the stage n was different, but still the nature of your action is the same. You actually do the same.
So let's say like bubble sort or some kind of
Dijkstra algorithm. You always
yeah,
do the
Dijkstra.
same stuff. It
Yeah.
doesn't depend on your state. So your state doesn't affect your actions.
Right.
This is how I understand this. And for your question, I admit that I never use dynamic programming algorithms, but I tried to once or twice. I tried to fine tune a language model with the RLHF, or reinforcement learning with human feedback, which is some kind of continuation of dynamic programming. It is dynamic programming, quite complicated part of it, quite complicated and sophisticated prolongation. Let's define it like this. But I never used the dynamic programming algorithm in its pure form.
Got it. And you near maybe doing control theory, or I don't know if you did actually.
I mean, outside the well-known, not in the purest sense of dynamic programming. No, I never used it. I mean, I can draw analogies to Kalman filtering and other type of iterative processes, and maybe that will degenerate the process to one policy that you always take regardless of what's the input and the output, and you don't try to optimize per policy at each stage. Maybe that's the criterion for pure or true dynamic programming. I don't know. I to be honest, I never actually read about dynamic programming like it's conveyed here in this paper until Daniel, you send us this paper, which is, I think, a beautiful paper. What further research from my part will be, first of all, I want to dive into this theory, mathematical theory, more. It's just time that doesn't permit me right now to do it. And there is in this paper, for the listeners, a lot of references of examples that he is giving in this paper that he's not deriving. It's referenced in the paper. So I would like to dive into these examples as well. And maybe, throwing the hat in the ring, so to speak, or the towel in the ring, if there is a listener that is an expert on dynamic programming, I would like to contact them to contact us or me and see how I can learn more about that. Maybe propose a course or a or a book on this.
Yeah, we might have a shared friend who might be relevant.
Okay.
So we'll see. We can talk to him, and I would just add to our listeners before we conclude that this, let's say, paper was our first introduction to more the reinforcement learning part of where we're going and where we're heading. And I also add that I am also far from being an expert, and I know the basic stuff around this area. So I'm enjoying also getting back to the beginning, let's say, and going with history and getting acquainted with all those concepts and how they were formulated for sure. So I would say keep tuning in because we'll have more papers. Again, some in this direction, some in others. We're doing some kind of exploration in this podcast. And at some point, we'll get to the paper that introduces those concepts. And any final remarks, Mike, Nir?
No, I just remember because my first degree was in mathematics and computer science, and actually I did a course on dynamic programming in Moscow. I guess it was 30 years ago, and I remember nothing from this from this course. But
Too
at the
much partying in Moscow.
time, yeah. Too much alcohol and
Hey, that,
Yeah.
they,
let's
Daniel,
put it this way. And but since then, 30 years, and I never touched this fascinating theory. And if I have time, I never have time. But if I have time, sometimes, and then maybe more closer to my retirement, I will study this subject for sure.
Cool. Unir, final remarks.
nope.
Cool. So thank you for your time. Keep on lifting heavy weights. Read math papers and enjoy life. And we'll see you next time.
Bye,
Bye
guys.
bye. Stay tuned, guys.